All right, today we're going to pull back the curtain and look at the hidden battleground that's raging inside all your electronics. We're talking about how these components are literally tortured, all to make sure they can survive out here, in the real world.
Yeah, have you ever really stopped to think about that? Your brand new phone? Why doesn't it just, break? You drop it, you leave it in a hot car, it freezes in the winter, and somehow it just keeps on ticking. How is that even possible?
Well, the secret is that long before that shiny new device ever gets into your hands, its most vital parts have been pushed to their absolute breaking point. Yeah, it's a pretty brutal process, but it's totally essential.
So this is what we're talking about. This is a printed circuit board, or a PCB. And yeah, it might not look like much, but this little green board is basically the nerve center, the city grid for the electricity, inside almost every single electronic device you own. It's telling every little part what to do and when to do it. So you can imagine, if this fails, the whole thing fails. So the big question is, how do we make absolutely sure it won't?
And that leads us right into the science of survival. See, there's a whole field of engineering dedicated to making sure your devices can handle a lifetime of stress. It's all about reliability.
Now, the textbook definition is the probability that an item will perform its intended function for a specified time interval under stated conditions. Okay, what does that actually mean? In plain English, it's about predicting the future. It's the science of making sure something doesn't just work when you take it out of the box, but that it's going to work for thousands of hours, under all sorts of crazy conditions.
Okay, and a great way to visualize this is something called the bathtub curve. It's basically a roadmap of a product's life. Right at the beginning, you have what they call infant mortality. These are the early failures, usually from some defect in manufacturing. Then, hopefully, you hit this long, stable, reliable period. That's the useful life. But eventually, everything starts to wear out. And that's the goal of all this testing, to find that wear-out breaking point in the lab so it never happens in your hands.
So yeah, the whole goal is to accelerate time itself. We need to find those wear-out failures in the lab before they ever get to you. The problem, of course, is that we can't just sit around and wait for years for a circuit board to fail naturally. We've got to find a way to simulate an entire lifetime of stress in just a matter of days, or maybe even hours.
So, how did they used to do it? Well, for decades, the industry standard was a method that was, pretty thorough, but man, was it agonizingly slow.
This traditional method is called thermal cycling, or TCT, and it's pretty much what it sounds like, a slow-motion torture test. You take the whole board, stick it in this big chamber, and just slowly heat it up and cool it down. Way down to -40 Celsius, then all the way up to 125, over and over and over again. Each cycle mimics the expansion and contraction that puts so much stress on all those tiny copper connections inside. But here's the huge, massive catch. Just look at that number. 288 hours to run one standard test. That's 12 days. In the world of electronics where things change in a blink, waiting almost 2 weeks for a single test result, that is an eternity. It's a gigantic roadblock to innovation.
So, you just knew there had to be a better way, right? A faster, smarter way. And there was. Engineers came up with a new method that was a total breakthrough.
And this is it. This is an interconnect stress test machine, or IST for short. And right away you can see it's not some giant industrial oven. That's because it takes a completely radically different approach to the whole problem.
So first big difference. Instead of testing the entire board, IST uses this specially designed little sample called a coupon. But don't let the size fool you. This coupon is engineered to contain all the critical connections, the vias, the plating, everything that you'd find in the full-size board. It's the perfect little stand-in. And here's the real genius move. Instead of heating the board from the outside with a bunch of hot air, IST heats it from the inside out. It actually passes a current through a specific power circuit. That's the yellow part you see here. And what this does is it uses the board's own copper traces as a heating element. The copper itself gets hot, super fast, stressing all those connections from within. Meanwhile, another circuit is constantly monitoring, listening for the very first sign of a failure. Honestly, the best way to think about it is this. It's a difference between slow roasting something in an oven versus feeding it up instantly in a microwave. TCT is the big, slow, inefficient oven. IST? It's the fast, targeted, super efficient microwave. And what that means is a single cycle doesn't take an hour anymore, it takes just a few minutes. And when you put them head to head, the numbers are just staggering. Look at this.
Time to get results? IST gets it done in 24 hours. TCT? 288. We're talking 1 day versus 12 days. The cost for each test is way, way lower, and on top of all that, it's better for the environment. I mean, it's a win-win-win all around.
Okay, so we're breaking things faster. But what does a failure actually look like? What are these tests really hunting for? To see that, we've got to go microscopic.
You have to remember, a circuit board is this really complex sandwich of different materials, all pressed together. And as it heats and cools, all those different layers expand and contract at slightly different rates. And that creates these immense internal stresses that can cause all kinds of tiny failures, things like barrel cracks or interconnect separation.
And this is so cool. Here we've got theory versus reality, side by side. On the left, that's the clean engineering diagram of what they call a barrel crack. Okay, looks neat enough. But then look on the right. That is the real thing, a microsection, a microscope image of that exact failure after an IST test. You can literally see that jagged crack running right through the copper wall. Incredible.
Let's look at another one. Here's a corner crack, which is another really common failure mode, because all that stress loves to concentrate in the corners. And again, you can see the schematic on the left and then the devastating reality of that cracked copper on the right. This is exactly what we're trying to do. Force this to happen in the lab so it never ever happens inside a device you're using.
All right, so this is all about reliability accelerated. We can break things faster and see how they fail. So what? Why does this really matter? What does it all enable?
Well, this is where a tool like IST really shines, because it gives engineers data fast. And what this chart shows is something super important. A board's survival. It's not just about, say, making the copper plating thicker. It's much more about the quality of the materials themselves, specifically how much they expand when they get hot. We call that CTE. A better material, one with a lower expansion rate, can survive hundreds and hundreds more stress cycles. And now engineers can figure that out in a day.
So when you can get that kind of deep, detailed feedback in 24 hours instead of 12 days, well, it completely changes the game. It allows engineers to innovate like crazy. They can try out new materials, test new designs, tweak manufacturing processes, and get feedback almost immediately. It's a genuine accelerator for innovation, leading to the more powerful and more reliable devices we all depend on.
So the next time you use your phone or your tablet or your laptop, maybe take a second to think about it. What unseen tests, what incredible microscopic battles has its circuit board already fought and won?